All right, so let's continue. Last lecture, we were at this particular point. We were looking at that MOS can operate in the following broad regions. MOS can operate above threshold, and when we are above threshold, we can divide its operating region into two parts. One is the linear region here, the boundary of which is defined by VD sat, the saturation voltage. And the other one is the region above that where the current varies little with the drain to source voltage. So we call that the saturation region here. So that's when MOSFET is biased above threshold. And then we were looking at when the MOSFET is biased below threshold. So we had seen the simple equations that are valid here. The current varies as square of the gate to source voltage here. The current varies. If you're at very small drain to source voltage, it varies linearly. For the subthreshold part, we said that if you look at the transfer characteristics, the drain current versus the gate to source voltage. So our threshold voltage is around 1 volt. So when we go above 1 volt here, we are above threshold and the characteristics is quadratic. VGS minus VT sort of square here. But when we go below the threshold, which is 1 volt again, the current on the linear scale appears to be very small, and you have to go to log scale in order to clearly see how the current varies. And so this is the picture that we had. So if you take the same plot, same data, and plot it on the semi-log plot, log axis here and linear axis here, we begin to see that this is where our threshold voltage is, around 1 volt. And this is the current. So as you go below threshold, there's a transition region around threshold where the current is neither quadratic, neither is it a pure exponential. But if you go, a little bit below threshold voltage, you begin to see that this particular graph becomes a straight line. A straight line on a semi-log plot indicates exponential variation here. So the current is below threshold voltage. We say current falls exponentially with the gate to source voltage here. And all right, so a simple expression then is that ID varies exponentially with VGS by some factor n dash KT here. And the MOSFET in this particular region, ID, if it's exponential, I can take its derivative with respect to gate to source voltage. So that gives us a transconductance del IDS by del VGS. And one can see here IDS by eta VT. VT is the thermal voltage here. And in this region here, the MOS, you can think MOS is acting, as far as the equations are concerned, like a bipolar. In a bipolar also, if you recall, the collector current would vary exponentially with base emitter voltage. IC equal to IS exponent VB by VT here. In a MOS, in the subthreshold region, IDS is some saturation, some constant current here, e to the power VGS by eta VT here. Okay, so they are both exponential characteristics. The advantage of MOS, of course, is that we have very little gate current, and therefore very high input impedance. When you look at it from the input side, you see an insulator. In contrast, in a bipolar, you see there's significant base current, right? So we had all that R pi and the resistances that are there here. Disadvantage is that in BGT, you get much higher current levels as compared to the MOS. We are below threshold. Remember, this characteristic is below threshold. Below threshold, the channel is weak. I don't have enough number of electrons, so the current levels are low. Okay, so you can go back and see the current levels here. You can see typical current levels that we have in this particular system here. Okay. All right, one can, of course, increase the current by increasing the size of the MOSFET, but the point is that the form is similar, the equations are similar, and therefore transconductance, if you recall, for a bipolar was collector current by VT, and here it is GM IDS by VT. So these are similar in nature, and but in terms of numbers, there are differences. The kind of current that you can get, the kind of transconductance that you can get in MOS are smaller. Nevertheless, it's a useful region which people do use for making amplifiers. Especially, you want to use this particular region here You can bias your MOSFET. It's acting like a bipolar. So if you want a very low current, low power circuit, let's say you want to make a differential amplifier which is very biased at very low power differential amplifier, you can take your MOS and bias it here. And very similar to a bipolar differential pair. Uh, but of course, transconductances and all are smaller, so the gain and all that will suffer. Okay. All right. So with this brief introduction to the MOSFET operation, so the model eventually, as we said, our interest is in using the MOSFET in circuits, to design circuits, to analyze circuits here. And the MOS model, very broad classification of MOS model that you can do is, you can talk about where the signals, by signals I mean voltages and currents are large in magnitude. And the other one, small signal, we understand what we mean by small signal, that you have a bias applied, and on top of the bias you apply a small perturbation, a small variation here, and you want to know how does the MOSFET respond to the perturbation, okay, to the small signal. So the small signal is on top of a DC, right? So that's what we understand from a small signal model here. Both of them you can talk about models which are low frequency, which is almost equivalent to a DC. And you can talk about a higher frequency model, or one may call it dynamic model or transient model, and all kinds of names are here. Okay, so one can divide the operation into low frequency and high frequency. Of course, as we had discussed earlier, one can think of one single model which is applicable for all regions of operation, all frequencies. But when we are analyzing circuits, that particular model becomes complex. And what we want is simple models to analyze and design, right? And that's why we segment our models into different regions in order to obtain simplicity. A general purpose model will become too difficult, too complex to deploy. And a model which is valid in smaller regions becomes simpler. Okay, so that's one reason why we do that here. Okay. So MOSFET, if you think in terms of a circuit, so far MOSFET we had a device. So if you think in terms of a circuit for low frequency operation, you can think of a MOSFET like this. Note that the MOSFET is 4 terminal: gate, drain, source, and the body. 4 terminals are there. Now, between the gate and the source, what do I have actually? I have nothing. Remember, between the gate, when you look at the gate, what do you have? You have an insulator. So in an ideal MOSFET, you don't have any gate current or negligible gate current. So that's why there's nothing here. It's like an open circuit. No current flows into the gate here. So when I'm talking about a DC or a low frequency model, nothing flows in the gate. The only significant current, if you don't, so there is a diode between the source and the body. If you recall, I have this, okay. So if you recall this, between the source and the body here, you can see a diode. So that's this particular diode here. Between the drain and the body here, between the drain and the body, again I have a diode, so you see this diode here. And as I said, we keep these diodes reverse biased. So the current flowing between here is some reverse leakage current, small current here, negligible here, and the current flowing here is also very small. So the only significant current that flows in a MOSFET is between the drain and the source. And we put it here between the drain and the source. So it's the diamond shape indicates that it's a dependent current source. The IDS we know has a dependence on, of course, drain to source voltage, but it also has a dependence on gate to source voltage. And it also has a dependence on body to source voltage. Would you agree? IDS is dependent on gate to source voltage, obviously. As I change the gate voltage, I change the channel charge, and obviously the current changes. Drain to source voltage is also obvious. If I apply a voltage across drain and source, it's the same pair of terminals, we know that current changes. In saturation, it may change a little, but in linear region, it changes a lot. So between drain and source. Why would the current change with body to source voltage? Why would the current change with body to source voltage? Gate to source, yes. Drain to source, yes. Body to source? What does body to source do? We keep it reverse biased. Okay, but what does it do? It it changes the threshold voltage. Body to source voltage changes the threshold voltage. And remember the current, for example, if it is biased in saturation region, current is beta VGS minus VT square. So the VT, the threshold voltage, it varies with the source to body voltage. So this current that I've shown here as a dependent current source, it depends on gate to source bias, depends on drain to source bias, and depends on body to source bias. Depends on all three voltages in general here. Okay. So if you want to think of a MOSFET, if you have a circuit and it's a DC circuit and you want to analyze, then this is what it is, a MOSFET here. And we have expressions for current. So all you have to do is decide now, is my MOSFET operating in saturation region? We have an expression for current in saturation. Is it operating in linear region? We have an expression for that. Is it operating in subthreshold? We have an expression for that as well. Right? So you have to decide which mode is the transistor working in and apply a appropriate expression for current, and then you have a first order description of how things are happening in the MOSFET here. Now, of course, each one of these models is simple. As I said, there are resistances. For example, in the simple picture, if you look at it, I have a contact here at the source, and from the source, I have to reach the channel. Right? And you go from the source to the channel going via N plus region here. Now, N plus is, has a certain amount of resistance. And between the metal contact that you put here, you put a metal on top of N plus, there is a little bit of voltage drop there as well. So what happens is from the source terminal, as you go towards the channel, you would find that there is a little bit of resistance there. So if I want things to be more accurate, I may put here, if I call this as the terminal, then between the terminal and the channel here, I will put a resistance at the source end. Some small resistance at the source, resistance at the drain. And similarly, body doesn't matter that much because there's not much current flowing through the body also. Okay, so one may want to put that. All right, so that's a DC model or a low frequency model. All right, frequencies are low. Now, how low and all that we'll see in a minute. Okay, so frequencies are low and DC, so you can use this particular model here. Small signal model. Again, if you recall from your E210, if I have a 3-terminal device, and also it's a unilateral device in the sense that the output gets affected by input, but the output does not affect the input here. So there is a direction in which the information flows here. So if we have a characteristic like this, any 3-terminal device, I can write a small signal model in this form. From the input side, it's like a low frequency again. It's like an input resistance Ri here. And from the output side, it is made up of these two elements here. Now note that these are actually very simple. All that we are saying is the output current depends on V0 and output current depends on Vi. And small signal models are nothing but whatever is the relationship between I0 and Vi and I0 and V0, whatever complex relationship is, what we do is we linearize it. For small signal, the relationship we linearize around a bias point. It's like a Taylor series expansion. You have a Taylor series and around a particular point you do an expansion, right? So it's similar. You have a current, expression of current as a function of Vi and V0, whatever complicated expression. Around a particular bias point, you are making a little bit perturbation, right? So you linearize it. And when you linearize it, you get linear terms. So what would happen is the small signal I0 would be made up of a linear term depending on V0 and a linear term depending on Vi, right? That's what would happen when you linearize it. A small current I0 depending linearly on Vi and linearly on V0. So a linear relationship between I0 and V0 is what? A resistor. And a linear relationship between I0 and Vi, how do you describe it? Well, you describe it by a dependent current source. Right? So it's straightforward why the small signal model looks like this. Now, if I had a 4-terminal device, let's say I have one I0 here and there's another input voltage here, V2, and this is V1. And now I0, let's say, depends on V1, V0, and V2. So if I linearize it, what will it look like? I0 depends on V1, I0 depends on V0, and I0 depends on V2. So if I linearize it, my small signal I0 will have 3 terms in it. One term depending only on V0, which will be like a resistor. Another term depending on VI here, V1 here, what will that look like? GM-V1. Another term depending on V2, what will that look like? GM, some GM2, V2, right? So my small signal model that you see will become like this. And from the input side, we are assuming input side, if you look at it, this would be some input resistance R1 here. When you look at it, this one here, some input resistance R2. We are taking this particular terminal as a common. So this becomes a small signal model for a 4-terminal device. All that we are saying is that this current here depends on this, and you just linearize it. So it will have 3 linear terms here. No, 3 linear terms. One R0, one GM1 V1, and one GM2 V2. If I had a 4 or 5 terminal, I would add one more thing here. Right? So, conceptually, the small signal model is actually simple. All that you are doing is linearizing it around a particular bias point. Now, if I had expressions for I0 as a function of V0, I0 as a function of V1, then I'll go through that linearization process, and out of that will come out what is the value of this GM1, what is the value of this GM2, what is the value of this R0. What are the expressions? I will get those expressions by if I have expressions for I0, V0, I0, V1 and all. Okay, so we'll not go through that process. So what we'll give you is a low frequency small signal model of a MOSFET. So everybody realizes now the only current that is flowing in a MOSFET first order is the drain to source current. There's no other current. Gate current is negligible, body current is also negligible. Okay, body is reverse bias. So the only current is drain current, and the drain current we said depends on VGS, body to source voltage. We are taking source as a common terminal and drain to source voltage. So when we linearize it, there will be 3 terms: GM, VGS, GMB, GM body, if you would like, VBS, and VDS by R0. So that's how your MOSFET looks like, small signal model of a MOSFET. Okay, the diodes are reverse bias, and reverse bias diodes small signal model under low frequency is just an open circuit. Reverse bias current first order does not vary much with the voltage, and therefore the reverse bias diode becomes an open circuit here. Reverse bias diode which was there also becomes an open circuit. So that's how your MOSFET looks like under small signal. And many times what we do is we keep the body and the source shorted together. Body and the source are shorted together, or the voltage is 0. So VBS will many times be 0. So you can remove this particular term, and what you end up with is GM, VGS, R0. That's it. Now, if you note that this is even simpler than a bipolar. In a bipolar, I had an R pi here. R pi, and we had GM, VBE, and we had R0. Now here we have GM instead of VBE, we have VGS, and we have R0. And body to source, we said keep it shorted, so this term is absent, and there's nothing in this side here. So now you have a small signal model of a MOSFET. So any amplifier, any circuit that is given there, and you want to do a small signal analysis, all you have to do is take that transistor out and substitute this particular model. And we have done enough of these small signal analysis with bipolar. So all these small signals that you have done with bipolar, the analysis here also is very similar. Note that the model is the same. GM, VGS, and R0. And in fact, simpler, I would say, because there's nothing on the input side. Right? So all the things that we did, they can be very readily, with the knowledge that you have, very readily you can go ahead and analyze any of those differential amplifiers. Common emitter becomes common source. Common base becomes common gate. Common collector becomes common drain. So there's a clear parallel between all the things that we did with bipolar. There's a clear parallel with what we do with MOSFET here. In digital, however, our interest is not so much in the small signal. In digital, remember, we are making a transition, we say from 0 to 1 and 1 to zeros and all that. 0 would typically be a 0 voltage, and 1 will be typically a VDD, right? So we are going from 0 to 3, or 3 is the supply voltage, or 3 to 0. So our interest is more not in the small signal, but our interest is in the large signal. You know, the transitions are large signal in nature here. All right. So these are the expressions. Expressions I'm not deriving. As I said, expressions will come from looking at the overall expression of current with respect to gate to source voltage, and you have to go through a process of linearization, and you arrive at these expressions. But these expressions are important. So it tells you how to compute GM. So GM, the expression is 2 IDSQ. Q, if you remember, is the quiescent point or the bias point. So small signal models are always valid around a bias point. So GM you can calculate using, if you know the bias current, DC current, IDSQ, VGSQ, you can calculate GM, or you can use this expression as well, square root 2 ID times beta here. All right. R naught is 1 over lambda IDSQ. Clear parallel to, again, bipolar. Bipolar was R naught was early voltage divided by IC. And we said 1 over lambda is like the early voltage for a MOSFET. So 1 over lambda is the early voltage for a MOSFET, 1 over lambda divided by IDSQ. The transconductance associated with the body to source voltage here, GMB, is related to GM through a factor eta here, and this slightly more complex. But note that once you know the bias point, and once you have information about your technology, so technology information will provide you with VTHN, will provide you with phi f, it will provide you with gamma, all these values here. So all these values will be given to you. Okay, so one can compute depending on the source to body voltage, one can compute eta, one can compute GMB, one can compute all these values. Okay. All right, now whenever we talk about small signal approximation, there's always an issue of how small. Now remember, my MOSFET, like bipolar, is in general nonlinear in nature. So the small signal is always an approximation. The linear model is except perhaps in a MOSFET, if you just go to, so linear model is in fact never valid, strictly, because these devices are nonlinear. So when you approximate a nonlinear model with a linear, there's always an approximation, there's always an error. And so the issue does arise as to how do the errors change with the small signal voltage here. Now note that the small signal approximation, the errors arise where? Because you're taking a nonlinear expression and linearizing it, right? So which is a nonlinear term here? If you recall, if I'm looking at the MOSFET in saturation region, the drain current varies with the gate to source voltage as quadratically. So it's a quadratic variation, and over a small region I'm approximating it by linear, right? So that's where the approximation comes in. Now how small depends on how accurate you want, and obviously you will realize that if you want a very accurate model, then the signal has to be very small. If you want even more accurate, you'll have to make it even smaller, right? So that's the kind of a trade-off between accuracy and how much voltage you can apply. Now if you go back and look at this model and the bipolar, in bipolar, note that this was the collector, and what was the relationship between collector and the base? This was base exponential. So in which case small signal model is more problematic. Here it is square, right? Note that in bipolar, typically this is exponential with base voltage here. So it's exponential is a very strong nonlinearity, right? Very small, strong nonlinearity. And so when you're trying to linearize it, if you don't want too much inaccuracy, you'll have to keep the input voltage fairly small. And we saw that voltage has to be considerably smaller than the thermal voltage here, VT. Base emitter voltage had to be much smaller than the thermal voltage VT. VT was 26 millivolt. And much smaller would become maybe 5 millivolt, 2, 3 millivolts and things like that. So in bipolar, if you want your analysis to be valid, you would like to keep it at 2, 3 millivolts, if for 10% errors and things like that. Here, note that this is not such a strong nonlinearity. If it is in subthreshold, then we are in the same situation. But if it is in saturation, that's where most of the analog circuits work. MOS-based analog circuits most of the time are in saturation region. So in saturation region, the drain current is not a very strong function of gate to source voltage, in the sense that the nonlinearity is not very strong. It's only quadratic. Okay, so as a result, we can apply a larger voltage here. A small signal voltage can be larger and still not have so much error here. So I just have this plot here, these numbers here, which will tell you the kind of things that I can do. So in a bipolar, I had to compare the small signal voltage to the thermal voltage here. Okay, in this case, I have to compare my small signal gate to source voltage with respect to VGS minus VTM. So this is my parameter here. In bipolar, I was saying base emitter voltage must be much, much smaller than thermal voltage. Here, we have to say VGS, small signal VGS should be much, much smaller than 2 times VGS minus VTM. Okay. And what are the errors? You can see here, I can apply VGS divided by this plus 0.1 and have an error of minus 4.7, minus 0.1, 5.26. So let's take this, or let's take this number. This is like 10% error. Okay. So what it says is, I have to apply small signal gate to source voltage divided by VGS minus VTN, which is 0.2. And then I'm within roughly 10% error here. Now, what is this VGS minus VTN? It depends on your DC bias. So let's say I've applied a DC bias of 2 volt. VGS is 2 volt, our threshold voltage is 1 volt. So VGS minus VTN is 1 volt. And small signal VGS divided by this has to be 0.2. So it says you can go and apply as much as 200 millivolt. You can go and apply in a MOSFET as much as 200 millivolt, and the errors would be about 10%. And in a bipolar, because of the exponential, I'll have to probably apply, I don't have the numbers here, 4 or 5 millivolts to get 10% error here. Alright, so it all depends on how strong the nonlinearity is. So MOSFET is not that strongly nonlinear in saturation and all that. And that's why the voltages that you can apply, as you can see here, are higher. Okay, so VGS, so this is the critical parameter here. And depending on the kind of errors that you want to tolerate, if you want to do more accurate analysis, you want to get more accurate numbers, you'll have to keep it maybe within 5%. So you'll have to keep VGS by VGS minus VTN as 0.1. Okay, 0.1. So if this factor is 1 volt, again, you can apply 100 millivolts. So still a very large value here, 100 millivolts. Okay. All right. Okay, so far we've talked about NMOS. Let's quickly talk about the PMOS part here. So PMOS, we said in our technology, we have a P-type substrate. So PMOS will create an N well, and we'll make a PMOS in that particular well. We'll have our P plus source, P plus drain, and we make a contact to the body. We make an N plus region here to make a good contact here, and the body contact is over here. Okay. Now note that the PMOS is complementary to NMOS in terms of, for example, the voltages and the currents. In a NMOS, I had to apply a positive gate voltage to create a channel of electrons. Here, I have to apply a negative gate to source voltage here to create a channel of holes. Now, in a NMOS, I applied a positive voltage to attract the electrons to the drain here. Now here, I will apply a negative voltage to the drain with respect to the source to cause the holes to flow. So we want the holes to flow from the source end and go to the drain end. So I'll apply a negative voltage to the drain with respect to the source, and then the holes flow into the drain here. All right, so these differences, please note, drain to source voltage typically is negative. Gate to source voltage, again, I will apply negative. Okay, and body and source, as I said, you have to keep body source junction either zero biased, so you short the two together, or you apply body to source voltage, which is body is positive with respect to the source side here, so that the junction is reverse biased here. Okay, so VGS is negative. Threshold voltage VTP, threshold voltage of P is we are talking about enhancement mode devices, so VTP is also negative. VDS is negative, IDS is negative. Okay, so now what do I mean by IDS negative? So if you see, if I apply a negative drain voltage here, the holes are going to flow like this and come out. And many places we take the direction of current as going into the terminal as positive. So current going into the terminal is positive. So that's why we'll have, according to this, the current is coming out of the terminal, drain terminal. So that's why we are saying IDS is negative. Okay, so if you compare the NMOS and the PMOS. Now usually what happens is, in all of these are typical discussions, we spend a lot of time with NPN. We don't spend as much time with PNP. We spend a lot of time with NMOS. We don't spend as much time with PMOS. So what we find is NMOS people can handle very comfortably, because all the time we're talking about NMOS. PMOS, we see people making errors. Okay, so it's important at this stage. Although in subsequent discussions we'll always find that most of our circuits would be complementary in nature. So we'll have N and P simultaneously there. So note that typical NMOS, gate to source, again I'm emphasizing positive here, drain to source is positive here, the current flows down from drain to the source. In PMOS, gate, drain, and source. So gate to source negative. Again, if I take source as a common terminal, gate to source negative, drain is positive with respect to this, current is flowing here. Now, a simpler way of doing this is if I compare the two. So again, talking about gate to source being negative and drain to source being negative, what we can do is the following. Take our PMOS and draw it like this. Right? Instead of drawing a PMOS, normally NMOSs you will see will draw with drain up and source down. And it's convenient, current is flowing down and things like that. Positive terminal is up and negative is down. So this is a convenient way in which we draw a NMOS here. PMOS we can draw also like this, right? Because if we draw like this, then the current is flowing up. All right. So if we redraw it in this particular manner here. So note that now it's like current is flowing from source to drain, which is fine. And note that instead of saying gate to source is positive, now you can also talk about alternatively source to gate is positive. Right? Source to gate is positive. Instead of saying drain to source is positive, we say source to drain is positive. And instead of saying current is flowing from drain to source, we say it's flowing from source to drain. So with this, if you compare the two, all that I need to do is, all the equations that I derived for NMOS, they are valid for PMOS also. All I have to do is, instead of talking about VGSN for N-type, I replace it by VSGP. So gate to source voltage has to be positive for N-type. Here is source to gate voltage positive. So wherever you see VGSN, you replace it by VSGP. Wherever you see IDSN, it becomes ISDP. Current flows from source to drain. Wherever you see VDSN, N-type, you replace it by VSDP. So you make these changes and your equations will all be valid here. VTHN will become minus VTHP. And so note, we had an equation in saturation like this for N-type. So all that we do is change the subscripts, of course, to P. IDS becomes ISD. VGS becomes VSG. VTHN becomes minus VTHP. VDS becomes VSD. Right? And the same. This current is positive. This voltage is positive. VTHP is negative for a PMOS. So effectively note that and VTHN is positive. So both are of the same nature here. And VSD is positive. Okay. So one can do it in this form. Small signal models, let me not, a small signal model of a PMOS is exactly the same as the NMOS here. If you recall, small signal model of the PNP was exactly the same as NPN. Okay. So same small signal models are here. All right. So we've discussed the small signal model of NMOS, small signal model of a PMOS, a large signal model here. What remains now is if you are analyzing things at higher frequencies, or if you're doing transient analysis in which the voltages and currents are changing rapidly, then what we need to do is we need to add capacitances to our model. And let's look at the capacitance. This is extremely important for our digital circuits here. So again, a simplified description of NMOS is given here. And what I've shown here are 5 capacitances here. 5 capacitances that you see. Okay. The first capacitance that let's talk about is between the gate here and the source terminal, between gate and source. All right. Now, just keep in mind, what is the capacitance? If there is any charge in my system, and as I change the voltage and the charge changes, it will give rise to capacitance, right? Del Q by del V. Now, note that if I look at for example, the gate to source, why is there a capacitance between gate and source? If you ask yourself. Well, let's consider, there is a channel, right? There's a channel that is there in my device here. And let's talk about saturation for a moment. There's a channel of electrons here. As I change my gate voltage, does the channel charge change? Does the amount of charge in the channel change or not? Yes. I mean, if I apply a higher gate voltage, I'll have more charge in the channel. If I apply less gate voltage, I have less charge in the channel. So as I change my gate voltage, the channel charge has to come and go, right? It has to come and go. And where does it come and go? These electrons come and go from here, from the N plus that you see here. So when I apply a gate voltage here, if I increase the gate voltage, I want more channel charge in the channel. Where does it come from? It comes through the N plus here. and I will create more positive charge here. So you can clearly see that I will have a capacitance between gate and source, because there's channel here, and as I apply gate voltage here, the charge changes with respect to the channel, with respect to the voltage that I apply. So charge has to come and go, and capacitors have to be charged. That's one reason. The other reason is normally that you see here, and if you're a little bit careful, you will see that there is an overlap between the gate and the N plus. I've shown an overlap between the gate and the N plus. All right. So even if there were no channel, let's say, even if there were no channel in my device here, I have overlap between this, and gate is like metal, and N plus also acts like it's a highly conductive region here. So you see that there's a parallel plate capacitance because of the overlap, right? So there's another contribution to it, which we call as the overlap capacitance. So gate to source, remember, is coming about because of channel part here, and is also coming about because of overlap between the gate and the source. Now, this one should be obvious. Source to body, what do I have? A diode, a PN junction diode. It's a reverse bias diode. A reverse bias diode has a capacitance in it. So that is obvious. Similarly, between drain and body, there's a diode here, so it's a reverse bias diode. So that's also obvious. Now, between gate and drain, well, now this is a little bit interesting. I can't go into the details. So again, there is an overlap that you see here between the gate and the drain here. So CGD has an overlap part. Now you may be wondering also that it may have a capacitance coming from the channel. But remember, once you go into saturation, so I'm talking about now a slightly simpler picture. Once it goes into saturation, any change in drain voltage, does it change the channel charge? Remember, you create a pinch-off region, and then pinch-off region slightly moves. So the first order, any change in the drain voltage actually doesn't do much to the channel charge. So the channel does not contribute much to the gate to drain capacitance in saturation. On the other hand, if I had linear region where the channel exists all throughout, then the channel will also contribute to gate and drain. So the capacitances depend on which region is the MOSFET operating in. Linear region, these capacitors will not depend. Source to body and drain to body, they're like PN junction capacitance, is fine. But gate to source and gate to drain, they depend on the region in which I'm operating. Linear region, saturation region, cutoff region. So they are there here. All right, so let's look at the gate to source. So I'm giving you now expressions, and I'm not going to justify the details of the expression here. So CGS, note that it has two values, two components of CGS. One part is 2/3 Cox W into L. W is the width of the MOSFET, and L is the length here. And don't ask where is 2/3 and all that, but this is the charge. This is the coming from the channel part. Channel, because of the channel charge. And this is coming about because of the overlap. So interestingly, what we do is, when we talk about the overlap part, so we define a capacitance, which is normally, note that this capacitance is defined as capacitance per unit length rather than area. Okay. So all that you need to do is note that the overlap part, the amount of overlap is a constant. You know, depending on the technology, there may be some amount of some nanometers of overlap between the gate and the source. So that overlap part is fixed. How much overlap capacitance I will get depends on what is the width of the MOSFET here. So this capacitance is specified in terms of the width. So this capacitance units are whatever picofarad, femtofarad per meter. So this is defined as, so this is a parameter that will be given to you as part of the technology. Once you choose a technology, you know what is CGS0. Okay, so this is given to you. And depending on the width of the MOSFET, you multiply together and you get this term. And the first term is area dependent. So Cox will also be given to you. Depending on your width of the MOSFET, your length of the MOSFET, you multiply it together and you'll get the CGS value. So it has two distinct components here. The channel part and the edge part here, that is there. CGD, on the other hand, these are first order models. CGD, on the other hand, is in saturation, is simply overlap times W. The channel does not contribute to the gate to drain capacitance in saturation. All right, so this is the picture that we have. If I look at a MOSFET, very simplified view from the top, right? So this is my gate here, L. This is my width of the MOSFET here. And this is my source that you see here, source region here. This is my drain here. Let's suppose the length of the source is LS, the width again W. So we'll see more better layout of a MOSFET later on. So there's a simplified layout here. All right. So MOSFET, if you look at it from the top, a region which is N plus, source here, a region which is again N plus, drain here, and in between is the gate. Right. So this is the area that we're talking about, W into L. W here and L here. Now, so we have two capacitances, CGS and CGD, right? And now let's talk about source to body and the drain to body. So now when we talk about source to body and drain to body, before that, a little bit of digression. Capacitances in general will have, you know, we think of a parallel plate capacitances, will have an area and a perimeter component. Two components here. What do I mean by that? All right, look at that. Let's suppose I take two plates here. Of course, there are field lines here, right? And you also know that there are fringe fields that are there here. Now, if I want to describe the area of this particular, and these are these two plates here, two parallel plates. If I want to describe the area of this one, note that this part here, the main part here, will scale with the area, right? Will scale with the area of the plates. Right, so this is this part here, standard capacitance that you know, epsilon by d, W into L. What about the fringe part here? The one that comes due to the fringe field. That's not going to scale with the area. Fringe is along the perimeter. So that will scale with the perimeter here. Right, so capacitances in general will have an area component and will have a perimeter component coming about from the fringes side here. And perimeter, C perimeter into perimeter is 2L plus 2W. Okay. Now note, if you're wondering, did we include the perimeter in the previous one? Go back and see here. Did we include the perimeter? See this, what is this here? CGSW. It's like the perimeter here, right? It depends only on the W. Only on the W here. Right, so this is the perimeter part here that you see. Okay, we will come to the perimeter part more here. So keep this in mind. So when I take a parallel plate, this is very, very important because you can imagine that if the area is very large, what happens is if you look at, if the area is pretty large, then the first term usually dominates. And the perimeter part does not matter here. But as the area gets smaller and smaller, so imagine that both W and L are the same. So this is epsilon by d L square. And this is whatever is a perimeter component multiplied by 4L, L by L, that's right. So as you scale the device, what happens is the importance of this particular term becomes larger and larger. And for actually very, very small devices, this term actually begins to dominate. The capacitance is dominated by the perimeter rather than by the area. All right. So, you know, for example, in digital circuits, when we talk about a metal line and all that running from one place to the other, the metal lines can be very, very narrow. Metal line running on top of a silicon dioxide, the metal lines may be of very narrow width. So the capacitance of that particular metal line will have an area component, but the perimeter component would be, if not more, maybe equally significant. All right. So this is a term that simply cannot be neglected here. The capacitance that is coming from the perimeter part here. Okay. So why am I coming here? Now, if I look at this particular capacitance here, this has an area component and this has a perimeter component here. Note, can you see look at this N plus region here. Can you see the perimeter? There's a perimeter here, LS, W and all this perimeter that is there. And there is the area component here. And why did I shade all this? Note that shaded region, which means outside this N plus region here, everything is oxide, covered with oxide. Why do I cover with oxide? We'll see later on. So we have one transistor here and surrounded by oxide here. And to isolate one transistor from the other. Okay, so all around is a silicon dioxide. So note that when I talk about capacitance here, the capacitance here would have two components. Source, so I'm talking about source to body capacitance. It has two components. It's a PN junction capacitance, but two components. One depends on the area of this region here, area of the source. And it's like a PN junction capacitance that you're familiar with. with some CJ 1 plus VSB by, this is built-in voltage here, and grading coefficients and all that. So these are parameters that will be given to you. CJ, PB, MJ will all be given to you. So you all know that. So depending on the source to body voltage, if it's 0, you put 0 here, and you can calculate depending on the area of the source here. And then there is a perimeter component. Now perimeter, if you note, I'm only looking at LS, W and LS here. There is no another W here. Because this sidewall has already been included where? This overlap between gate and source in the CGS and CGD. Remember, this part was already included here. This, I said there's an overlap here. So this is this particular term. Okay, depending on W. So that does not come it's not a PN junction capacitance here. The overlap here is like a parallel plate capacitor, and we have already included this wall here. But this, and this. So we call this edge capacitance as you can see here, the name as side walls. It's like a wall of, it's like a wall here, and wall here. These are called side walls here. So these are the perimeter capacitance here. So perimeter is 2 LS plus W. 1 LS here, 1 LS here, and 1 W here. So that's the perimeter part here. And as I said, these values will be given to you. What is this CJ sidewall? What is this? What are these numbers? And MJ sidewall and all that? They are all technology parameters. They're all either derived from, most of the time these are all measured experimentally, and these are available to you. Okay? And so all you have to know from a designer's point of view, you have to know what is the area of the source and what is the perimeter of the source. Because area and perimeter will decide how much is this capacitance source to body. And same thing, whatever I've said about source to body applies to drain to body also. Is the same thing here. Except that, note that drain to body voltage will be different. Drain to body voltage will be different. Otherwise, the expressions and all that are exactly the same. Okay. Now, I'd like to stop here because next week is our mid-sem. Right. So we have exams coming up. And the syllabus for the exam, as I said, is everything before the MOSFET. So the last topic that we covered before the MOSFET was static timing analysis. And before we leave, there's a little bit of, there was one issue raised by a student regarding something that we had discussed here. Okay, so a little bit of clarification is needed regarding this particular diagram here. Okay. So change your mind to now from MOSFET to this RTL, right? Go back to this RTL. So if you look at this particular diagram, we had said that we have all these operations and we schedule it and all that. Remember, we were saying that, of course, to do any of these additions and all that, we have to load. We have to load read the data into the registers. And the reading part we were not showing explicitly. We were saying, well, we'll add it later on and all that. We were not showing it explicitly. And when we were talking about these states here, we said, well, I require A here and B here. We had diagrams like this, A, B, C and all that, right? If you note in this diagram, what we have done is this Y, Y, we have put it here, right? But note that Y is produced here. Now, where do I have to store Y in the next, if let's say this operation is taking place in this clock cycle, I need to have a register available in the next clock cycle to store Y, correct? I don't need a register here. I need a register in the next clock cycle because that's where the transfer takes place, as we discussed here. So I need a register to store Y. And I took this Y and I put it here. In many of these diagrams that we drew, we put it here. So what does it imply? After this clock cycle, what comes? We come back here, right? So, which is fine. There's nothing wrong. What we had implicitly, in all this discussion we had done, but I've been saying that there is a load here required. So implicitly what we had in this particular diagram was a sort of loop pipelining was sort of assumed. Because note that if I add before this a load cycle here, where I read the data, where would this be available now? In the read part, right? So in the read part, so where the confusion was that all these diagrams are correct, but they imply that I will eventually store Y in this particular cycle. So as an intermediate step, we said, okay, we need to add this. But remember that this is sort of a redundant state. because all that you're reading, very quickly you can see here that if you add this particular part can be folded back here. Right? So this part, R3, R5, R5 plus R4, which goes into R5, can be folded back into this particular place. Right? So this you can take it out and fold it back here. And then the diagrams are all consistent. So this was a sort of an intermediate state that we had put in between. And I think we had, not explicitly talked, we had said about loop pipelining and all that, but in this diagram we had not talked about. So because this is creating a bit of confusion, because if we have this and we say Y is folded back here, which is not true, right? Because if you add this particular state, then Y is available in this particular state, not here. So this is sort of there's nothing inconsistent between this and this. This diagram is still correct, except that it uses a unnecessarily extra register is being used, which we saw in the quiz. As all of you, when you did the quiz, you found that it has extra registers and you can reduce it, okay? So remember that when this diagram is drawn actually for this kind of thing here. So sort of, and implicitly it has been assumed that yes, there is a load, there's a cycle where I would load, and the last one that you see here will be folded back into the load. Okay, so this diagram is for this kind of a ACM chart description, not for this one. This is an intermediate step that you can add and quickly take this particular part, fold it here, and arrive at this. Then there is no inconsistency. But if you look between here and here and drawing Y here, then there is a problem. Y is not required here. Y is required in the upper cycle here. Okay, so so this is a intermediate ASM chart, which is obviously nobody will really use this particular one because it's wasting a clock cycle. It's simply you're reading it. So what would normally one would do is take this and fold it back here, and then you don't waste a clock cycle.